Dave. Okay, so finally we're at the final presentation of this session, which is a keynote talk by David Che. So David Che received his bachelor degree from University of Waterloo in '89 and his PhD from LIDS in '94. Now, David has such a long CV that in the interest of time, I'll only read something that, I mean, every time I read it impresses me enormously. So he has the insane number of only the paper awards, the technical awards. So let's read through them. 2 Best Paper Awards at the Infocom in '98 and 2001, the Erlang Prize in 2000 from the Informs Society, the IEEE Communication Society and Information Theory Joint Paper Award, not once but twice in 2000 and 2013, IT Society Paper Award 2003. Now you're counting societies, right? So this is Signal Processing Society Best Paper Award in 2012, EuroSIP Best Paper Award 2012, and Communication Society Stephen O. Rice Prize in 2013. Now what's sort of what's amazing about this is that, you know, all of these societies are very sort of focused on very distinct and different things, and somehow David managed to be the top master of all of this. And today he will, in his talk, he will talk about something completely new and different from either of this. So let's welcome David.
Thank you very much, Yuri. So it's so great to be back here. So thank you very much, John, for inviting me and organizing the event. So I hear an echo of myself. Sorry? Is it because of that? Can we turn this one off? Okay. Just stand away. The problem is I'll have to go to the computer a bit later. Okay. All right. So congratulations, Bob and Dave, for the honor. It's so great to be here in the same session. Okay. So as Yuri really nicely summarized, LIDS, we started off with completely whiteboard, no, not whiteboard, sorry, blackboard at that time. And somehow we were able to make some impact on the real world. And I think we were very fortunate in the sense that during those 30 or 40 years that you were mentioning, there was a huge progress in infrastructure building, in particular communication infrastructure building, going from wireline to wireless. And we're very fortunate to catch those waves. And so I think whenever there is an infrastructure building opportunity, there's an opportunity for us to make an impact. And so today, I think Yuri told me to talk a little bit about the past. Frankly, I don't like to talk about the past because we can't change the past. We can only change the future. So I'm going to talk about what I'm doing right now. But hopefully from hearing what I'm doing right now, you get a sense of how it connects to the past. So what I'm going to talk to you right now is, I feel, another infrastructure building opportunity. And this is in the blockchain area. So infrastructure building usually starts with a breakthrough. And in this field, the breakthrough is done by this guy. His name is Satoshi Nakamoto. So he wrote this paper called Bitcoin, a peer-to-peer electronic cash system. Now you're looking at this and say, whoa, isn't like this about scam and money laundering and so forth? Why is this guy now talking about it? Has it gone to the deep end? So it turns out that, you know, technology you can apply in a positive way or negative way, but underlying this system that he created, there's a very interesting technology that he invented. And that technology is much broader than just the specific Bitcoin. And this technology is called blockchain. And really, blockchain is an infrastructure for decentralized trust. And if you think about it, trust is really something that is the center of human society. And what this guy accomplished was to able to build infrastructure to maintain decentralized trust without a centralized authority. This is probably the first time in the history of mankind that this kind of infrastructure has been built. And so this is the infrastructure. So let's look at the performance of this infrastructure. Okay, so there are 3 important performance measures of a decentralized trust system like Bitcoin. The number 1 is security. So when you want to build a decentralized trust system, you want it to be so trustworthy that even though an adversary can attack it, it cannot change what this trust system maintains. So what does a trust system maintain is really a ledger, a record of history. It is a decentralized trust system because it was able to create this record so that nobody can change it unless you are super powerful. And what he showed is that unless the adversary has 50% of the power of the whole network, no one can change history. Okay, so that's very good. However, the throughput of handling transactions, so it's keeping record. So each item of the record is a transaction. In the case of Bitcoin, it is a record of who pays how much to whom. The throughput is very low, 7 transactions per second. Just a comparison, Visa can have 10,000 transactions per second, so we are very low. Number 3, very importantly, is the confirmation latency. How long do you have to wait until you trust that information is entered into the record and can never be changed? And this latency is of the order of hours in Bitcoin. So again, very poor. And so if you look at this from an infrastructure point of view, you will find that whereas it is a very solid, very secure, decentralized trust system, its scalability in terms of throughput and latency is very poor, very poor. So very poor means good. There's opportunity to make progress. And in the past few years, lots of people have been trying to make progress on the 2nd and 3rd number. However, the problem is not solved. What people observed in the past few years is that there is a curious phenomenon. Some people call it the blockchain trilemma. And this trilemma basically says the following. In a decentralized trust system, decentralization is very important. That is, the power should be spread across many, many different participants. Security, as we mentioned, is important. And scalability is important. And the goal, the holy grail, is to try to accomplish all 3 of them simultaneously. But existing systems can typically achieve only 2. For example, Bitcoin can achieve decentralization, security, but not scalability. The throughput is very low. And there have been other efforts that try to get scalability, but then they lose in security. And other efforts tries to get security and scalability, but at the expense of centralization. So the state of the field is that there are many projects, many efforts, but none have achieved all 3 at the same time. And so what we accomplished in the past year is to find a protocol that simultaneously achieves all 3. And we call it the trifactor, which stands for 3 times good, or 3 times perfect. Okay, so what I'm going to do is I'm going to show you how this protocol works, and then we will go back to some theory. Of course, we have to go back to some theory, right? This is LIDS. Okay. Okay. So I'm going to try to visualize the protocol. Okay. All right, so first let me visualize how Bitcoin works. Okay? So Bitcoin works the following, that there are many nodes in the network, and each node solves a very hard math puzzle. This puzzle is a cryptographic puzzle. When it succeeds in solving the puzzle, it is eligible to put a block into this chain of blockchain. And the blockchain is connected together through these cryptographic puzzles so that they cannot be changed, okay? And each block contains transactions. Each block contains transactions that enters into the ledger. So whenever a block goes in, it enters a ledger. So what's happening here is that there are two things going on here in this blockchain. Okay? First, transactions are entered into the ledger. Second, each block implicitly vote for the previous block. And the point is that as you get more and more, as a block gets more and more deeper into the blockchain, then it can then get confirmed. So the main parameter of interest on the blockchain is a so-called mining rate. This is the rate at which the puzzle gets solved and the rate at which blocks get generated. So in Bitcoin, one block is generated every 10 minutes, So that means every 10 minutes, there's a block, and this simulation is faster. This visualization is faster. Of course, it's faster, right? If I wait a block every 10 minutes, then Yuri will be quite worried. Okay. And I don't want to worry Yuri. You're worrying me. Okay. All right. So, therefore, the trick is to speed up this whole thing so that I can finish the talk quicker. What we should do, therefore, very simple solution is what? Is to make the mining rate, or the rate, oh, I think I got the wrong visualization here. No wonder it doesn't work as I said, okay. So, all right, let me start again here. This is software that Bob likes so much, All right, so, okay, so blocks get generated. And now what happens is as I increase the mining rate, what is happening here is that the blockchain experiences the so-called forking. Okay, so why is it experience forking? Because remember, we are in a decentralized network, and people are mining blocks. If they succeed in mining a block, they will push it out and broadcast it to the rest of the network. And the problem here is that as the mining rate increases, because of the delay between nodes when they hear each other, then simultaneously multiple blocks get mined on the same block, and you have this forking. And what does forking happen is that the growth rate of the chain, the longest chain, slows down a lot because of the forking. And that reduces the security of this blockchain. And so therefore, increasing the mining rate does not really solve the problem. And here you can see that really what happens is that there's a trade-off between scalability and security. Because as you try to increase the throughput, you reduce the security. And so that's one reason why that trilemma is rather difficult to solve. Okay, so what we did when we look at this problem was to say the following. Okay. Okay. So what we did was to say, okay, so I need to increase the mining rate to try to speed up the confirmation and speed up the throughput. Okay, so I'm trying to speed up two things. But I can't just increase the rate like this because you experience forking. Okay? So what we did was we separate out, decompose the problem. That's one thing that LIDS teach me. Whenever you have a very complicated problem, try to break it down into a simpler problem. So the first, we try to solve the problem of increasing the latency. Increasing the latency. So how do we do that? To increase the latency, what we're trying to do, if you look at the situation, is that the problem here is that if you look at a particular block, it is waiting for later blocks to come in and vote for that block to confirm it. The voting rate is very low because you have one vote every 10 minutes. So we want to increase the voting rate, but we can't increase just the mining rate directly. So what we did was instead of increasing the mining rate by increasing the speed of this chain, what we did is we create two types of blocks so that we have the blue block and the green block. And what the blue block does is its only job is to vote for those green blocks to confirm it. So this way, these blue blocks all lie in a chain, and then they can vote for these green blocks, and that speeds up the voting rate a lot. In fact, here, for example, if we have 1,000 of these chains, the voting rate gets increased by a factor of 1,000, and therefore can speed up the confirmation latency a lot. Okay? All right, so that improves the confirmation latency from hours to seconds. Okay? Now, however, the transaction throughput is still very low because these green blocks are still growing very slowly to avoid forking. So then we came up with a second idea, which is how to increase the throughput. Okay? So the way we do it is that we transform into a third type of blocks. So now instead of having blue blocks and green blocks, we have a third type of blocks. And these blocks contains transactions only. So we shift these transactions from these green blocks to this third type of blocks called transaction blocks. And now these green blocks' only job is to refer to these transaction blocks to bring them into the ledger. So this way, we increase the throughput a lot, without forking the central green blocks, and thereby increase throughput, increase confirmation. So the way we do it now is we start with a very simple blockchain, which is invented by Nakamoto. And what we showed is that to have scalability, you now, instead of having one blockchain, you have three structures. The center blocks, which are essentially the proposal blocks, the blue blocks, which are the voter blocks, which go as vote for a blue block, and then the transaction blocks. So therefore, we were able to solve the trilemma by essentially decomposing the problem into security and scalability separately, okay? And now we have no trade-off between the two. You can get very high security and very high scalability by separating out, by decomposing the structure, okay? Now, I call this vertical scalability. Because what we're achieving here is that we can now send transaction blocks at essentially the fastest speed available by the nodes. So for example, if the nodes have a communication length of 200 megabits per second, then these blocks can be generated at that rate, saturating the communication, okay? Now, people are ambitious though. They say, okay, maybe after I saturate the link, I still want to increase the throughput even further, okay? So we came up with a method to do that too, and we call that horizontal scalability, okay? So the last idea here is that instead of having a small number of nodes, now I'm going to increase the number of nodes and have different nodes generate blocks, transaction blocks of different color. And when you create the ledger, different transaction blocks, different nodes will create different ledger. So now the same system with the same security can now simultaneously run multiple applications simultaneously. And each one of them is essentially maintaining a separate ledger. So now you can simultaneously run a highly secure system, increasing the rate, okay? All right. So we actually implemented the system. We had a bunch of very talented students we work with. We wrote 20,000 lines of software. I have to, Bob, so, I was your student, and I admire you a lot. But I have to disagree with what you said earlier, which is software writing is not mindless. Okay? All right, so that's what I have to say. Okay, all right. So just before the talk, I started the software running, okay? So this looks like before, right? But before the visualization, was just a simulation. This visualization is now a real network running. So we have 100 EC2 nodes on the cloud running right now. And it is running this blockchain. And this is a real-time visualization of what's being run right now. So I'll show you the performance to see how far we can get from 7 transactions per second in Bitcoin to our system. OK. So here, I'm recording the transactions per second plot throughput of per node. So this is our network. I think there are 100 nodes in this network. Each node is an EC2 machine. And each curve represents the throughput that each node is experiencing. And here we're seeing that the total transactions per second, this has been running for the past half an hour already. The rate is around 250K transactions per second. Okay? This is the latency is 28 seconds. Okay? So we get it down to from hours to seconds, and throughput from 7 transactions to 250K transactions per second. So here you can see that we have 6 ledgers simultaneously being run right now. In a more technical term, each ledger is called a shard. Shard is a term that comes from database. So this is essentially we're running a decentralized permissionless database at this moment. Okay? So each shard is around 35 to 40K, adding up to 250K transactions per second. Okay? All right. You know, live demo is a bit risky business, you know. You go to a live demo, it may not even work. But I'm glad that it works today. OK. All right. Now, my advisors sitting there is probably thinking, oh, my goodness, what happened to this guy? we trained these guys to prove theorems. And now all he has is a software with a lot of numbers. Mindless software. OK? All right. So I understand that sentiment. So I figured I better go back to some theorems. OK. All right. So let's prove some theorems. OK. All right. So in this business, we have to prove theorems, actually. We have to prove theorems. And the reason why we have to prove theorems is because the performance I'm showing you, okay, is what is happening when there is no attack on the system. But what happens if there's an attack? I can simulate some specific attacks that I can think of. But you have to prove theorems to say that no matter what the attack is within a very wide model, the system still behaves properly. Okay? And so this is the beauty of this topic, I think, is that the software and there's theorems. OK. All right. So let's go to the theorems. So to prove some theorems, we first need to establish, OK, so what are the parameters of the model? How do we measure performance? And here, I'm trying to connect it to some physical limits of the underlying blockchain network. OK? So here, we have network capacity as one parameter, C, 200 megabits per second, and speed of light propagation delay, D, which is of the order of seconds. Typically, it goes through multiple hops. OK? So these are 2 parameters, C and D. So we're going to prove security theorems, which shows how secure our system is and how much throughput and latency we can get as a function of C and D. OK, so the security theorems. We proved. Number 1, we showed the following, that as long as the adversary has less than 50% of the power of the network. OK, so here, what does it mean by 50% power? I should be a little bit clearer. Remember that this blockchain is run by people trying to solve math puzzles, right? The faster your computer, the faster you can solve a math puzzle, and the faster you can generate a block, right? And so what 50% here means is that as long as the compute power of the bad guys is less than the compute power of the good guys, then my system is secure. Trifactor system is secure. Secure means it's consistent and live, okay? So these are languages coming from the distributed computing community, okay? Which means basically that, hey, you maintain a record and that record will not change, okay? Live means that you can keep on pushing transactions into this ledger. You won't stall, okay? All right. So this is the strongest result one can prove, because if your adversary has more power than you, then really there's not much you can do. Okay, the second theorem says that the trifactor can achieve k times 1 minus beta c throughput, where c is my communication bandwidth, beta is the adversary power, and k is the number of shots. So in that demo, in that prototype that I was showing, we have 6 shots, so k equals 6. Okay, so what does that mean? First of all, it is proportional to my communication. So I'm saturating my communication link. 1 minus beta, because the adversary has power beta, and it can do a DDoS attack. So 1 minus beta is kind of the best that you can do. And k means that you are getting simultaneously throughput adding up across the shots. Okay? Lastly, the latency is of the order of d, which is my propagation delay, plus a term that depends on how much guarantee you want to get, epsilon, divided by m, which is the number of voting chain. Okay? All right, so that's the result. Okay, so the first result says that you can get close to the fastest you can push stuff out. It is proportional number of shots, which is good. The second result says that the latency can be decreased by having more and more voting chain. Okay? So therefore, if you have a lot of voting chain, like 1,000, then your delay is of the order of the propagation delay. And that's why we're getting 20-something seconds. Okay? All right. Now, to prove these theorems, there are 2 kind of subtle points, and I want to point out. First, there is this k. Okay? So remember that we are maintaining the security of the system. Everybody is maintaining the security of the whole system. Okay? Now, each node is running the ledger of its own shard, processing the transaction and communicating. So achieving k times 1 minus c basically means essentially that across different shards, you don't have to communicate any information. Okay? So really, to achieve this k, you have to show that the minimal information you can communicate between shards while still maintaining security is very low. And this is an information theoretic question. And this question is called data availability. And it turns out that this problem can be solved using coding. Okay, so coding. Second, to prove this result, what we're doing here is essentially a large deviation analysis of some random tree structure. Okay? So these are the 2 types of math that goes into proving this result and this result. Now, the reason why I point out these 2 things is because I have 2 advisors. And here, I have an information theorist advisor. And here, it connects to coding. And here, I have a guy who loves to do stochastic analysis. And so I thought I would pay tribute to my 2 advisors by the 2 math results. And I was going to prove one of them, but time is running out, and Yuri is looking at me, so I'm going to skip all these slides. No worries. No worries. Okay. And then I will go straight to final thoughts. Okay? Okay, first, we're humans. Infrastructure building never stops. We finish one wave of infrastructure building, we start another wave. Whenever there's infrastructure building, I think, information theory, communication, networking ideas, still very useful. So we may not be talking about 5G, 6G, 7G, But this is another infrastructure, another type of generations. So we have a lot of very talented students and faculty collaborating on this project. We have 4 faculty here. Mohammed from MIT, Julia Fonti, Shriram Kannan, Pramod Viswanath from multiple universities. And we have multiple students, Ranveer, Vivek, Lei, Guru, and Sonsur, working on this project. Thank you very much.
So we have -2 minutes for questions, but we'll still, I guess we can take one quick question for Dave.
Yes.
How do shards help you? If I take 2 things in different shards, how do I know before?
Okay. Remember in that structure, there are 2 parts. There's security and there's scalability. The security is the proposal blocks and the voting. That is maintained by everybody. So in other words, everybody maintains the security, and therefore everybody is responsible for maintaining this ordering. However, the processing, each shard is only responsible for processing transactions within its own shard. So that's a division of labor. And so that's why I mentioned the data availability problem, because to maintain that ordering, but you have to somehow know that blocks of other shards actually exist, but you can't process it. So you need sort of minimal efficient exchange of information. And that's where coding comes in.
Okay, maybe one more question.
How might quantum information theory, quantum computing, and quantum computation affect blockchain?
Okay. So, I'm not a quantum expert. So the key to the blockchain is this puzzle that you have to solve, which is essentially solving a hash inequality based on this function called hash 256. Okay? So if you could solve this hash inequality very quickly, then you can break blockchain. Because the whole blockchain is relying on these hash to connect each up together so that you cannot change one of the blocks without solving the puzzle again. Okay? So if I understand correctly, hash 256 is, I believe, post-classical safe. But I'm not completely sure. That's my guess. Okay.
There was one more question there. Yeah.
Professor Vidyasagar.
You, in your latency result,
Yes.
said you use large deviation theory.
Yes.
One of the main weaknesses of large deviation theory is that you can never turn that O symbol into an actual constant. How do you think about that?
No, that's not true. That's not true. Large deviation actually gives you very sharp, can give you very sharp results. So the O results are all in the exponents. The constants are in the exponents. So large deviation, the prefactor may not be very sharp, but the exponents are very sharp.
Yeah, that's what I'm saying. The exponents are very sharp, but the constant in front is not sharp.
Yeah, but the constant in front only appears in log term in the latency.
Okay, all right, I got it. Thank you.
All right, maybe one more question, and then we have less coffee.
Yeah.
Blockchain architecture is actually independent of whether or not you have a cryptographic puzzle or not. There's another class of blockchains built, obviously, around consensus algorithms or smart contracts. There is also a third class that some of my colleagues have been working on in New York that actually do not deal at all with these types of crypto algos. You have a peer-to-peer type of communication here.
Yes.
Most of the ledgers actually really require dual entry accounting in their ledgers, so they need to have not only positive valued assets or being transferred in each of the transactions, but they need also long and short, or they may need also all sorts of additional collateralized and other types of book entries. And for that, actually the solution is a self-validating architecture, which is very fast, the order of 100,000 transactions a second and uses fractal lattice type of architecture.
Okay. I'd love to talk with you offline, yeah. Great, thank you.
All right, let's thank all the speakers in this session.